Hello, in this video, we will show how to classify the MNIST handwritten digits images using CNN in PyTorch. So CNN here means the Convolutional Neural Network model. So the core of a CNN model is for the convolution operation. So what is the convolution? Convolution means that we get the information patch by patch from the image. So this is the original image with a dog and with the surrounding picture colors. So for example, this is a 28 pixel for two-dimensional data coming in from the image, and after Python reading in the image, it comes with 28 pixel and 28 pixel in the column or the rows. Each value is between 0 to 255, for example. And we use convolution, which is a kernel field. So this kernel field, for example, is 3 by 3 or 5 by 5 pixel. Then this kernel move along the picture and get the information. And operation is just the weight. So this, if we have 5 by 5 kernel, so there are 25 weights parameters, right? Then this parameter times each corresponding pixel and with summation. So this is in the output of this convolution layer. And you can see the output feature map. So we call it feature map. Feature map is also two-dimensional output information. And this value and the size of this feature map is not necessarily the same as this one, right? So after this operation, we get information. Then we can have multiple feature map with different weights parameters. So for the original data, for the color picture, there are 3 channels, RGB, right? Red, green, blue, right? And we can have multiple, for example, 64 feature maps. And each feature map coming from a corresponding kernel, different weights. So you can see, compared with the previous video, we have introduced the full connected model for the machine learning, for the deep learning. This convolutional layer has much less parameters because there only one feature map in this example is only 25 weights, right? And of course, we add the BS. So it's much less parameters, but we get much focused information for the picture for different position of the original. So this is a win-win. We have less weights, but we get more information, different information for different fields. So this is the basic idea of the convolution layer. And if we look in this figure, you can see this is a kernel. This kernel, which means the weights, 9 weights here, this 3 by 3 kernel. So move along this original incoming this image layer, image channel. Also, this is one channel. For the black-white picture, only one channel. But for the color picture, there's 3 channels, like 3 such input image. So we add a padding area 0. Why we add a pad? Because if we do not add a pad, the bound area only be used once, right? Because this kernel use here, then move next position. So this the bounding area only used once. So avoiding this circumstances, we add padding. And sometimes we add padding 0 for the one line, one column for both sides, up and down. Then we can get the same size of the output. So this is called same for the padding. And this is the most widely used padding method. So in this example, we use the padding 0 and we get the same same size for the feature map for the output. And of course, output is also 8, input is also 8. And we have multiple such kind of outputs, 8 by 8 image information, right? So, and this picture shows the convolutions calculation. For example, we have 3 by 3 kernel. Then this is the input, and we add padding 0 for the side, for the up and down, left and right. Then from this kernel, the first position is here, this position. Then the multiplication with the parameter and the value and summing together, then we get this value in output. And next we move 2 position right. This is called a stride. So the default stride is 1 by 1, is 1. But here, this example, we use stride 2. So you can see the stride is 2, so the size of the output is not the same as the original one, right? Because we moved 2 one time. So stride and padding will decide the output size of this and compared with the input, right? So move this one, then get this one. And we move down, we'll get this value. And this is the last value. So this is the convolution calculation. And next we will show what is the pooling. So after convolution, we can also use another layer called pooling layer. So pooling layer has no parameter. It is just 2 kinds of operation. One kind is called maximum pooling and another called mean pooling. So usually pooling has the stride same as the pooling size. So pooling also has a kernel size. So here we use a 3 by 3, for example. So this is for example, the output of a convolutional layer and with a 6 by 6 pixel. And after pooling with a 3 by 3, you can see the result size is 2 by 2. Because we get this is the first pooling operation, and we get, if we use maximum, for example, we'll get 8. Then the result is 8. No any parameters involved. And this is the next pooling, we get 5. But if we use mean pooling, we'll get this result. And we will do the final result correspondingly for the pooling with the kernel size 3 by 3 and the stride also 3 by 3. So stride is the moving speed, and the padding is for the convolutional operation. But in the pooling, there's no padding, right? So this is the 2 most important operations, convolution and pooling in a CNN model. So after these 2, we get much information for the position of the original picture. We get the shape and which kinds of detailed information. Then we can use these kinds of knowledge to establish a model for classifying the MNIST handwritten digits with the CNN. So this is in this model, we use such kind of layers. So the first is incoming with 28 times 1. So this one is because this handwritten digits picture image is 1 channel for the black and white image. So only 1 channel. So this you can see the 3-dimensional array coming in, right? 28, this is height, and this is the this is width, and this is channel. Then after first convolution, we write this means the kernel is 5 by 5 and channel is 32. So you can see this is each field. So we get the output field, output 32. 32, this is similar as the channel because this is also the 3rd dimension. So we have kernel 5 by 5 and times 32. This is how many parameters for this convolution operation. Each 5 by 5 is a kernel, but for each different field, we have different parameters. So upon this, we can get the output of such kinds of size because we use padding with the same padding. So we add 0 around this image, then we'll get the same size after convolution. So this is output from first convolution layer, and the size of each field is 28. Then we have 32 such kinds of image information. Then after pooling, it is a smaller size for the output field, right? Because it's only 14 by 14 now, but how many fields is the same. Then next convolution, we use 5 by 5 kernel and 64 channel fields. So the result of the second convolutional layer output is 14 by 14 size of this information, then with 64 channel, 64 fields. Then after second pooling, we'll get the size of the layer is 7 by 7, then 64. Because the pooling does not change how many fields, how many channels. Then we will use flattened. So what is called flattened? It's very easy, just multiplication for all these 3. Because this is 3-dimensional, but we cannot use 3-dimensional for the classification of digits. So we have to flatten to 1-dimensional data, 1-dimensional array. So this is result is 1024 by 1. So this is only 1-dimensional array with 1024 value. Then we can use another FC, full connected layer between them. So you can see full connected layer has many, much more parameters than the former convolutional layer, right? Because they're full connected to between 10 and 1024. There are about 10,000 parameters for this layer. But here you can see each only have 2564, about 1,500, right? So this is, of course, we do not show the some information, because from this full connector we will use a sigmoid or softmax for the probability of each digit. Then we'll get the which digits from the highest probability, right? So this is the basic framework flow of this tensor. We call it tensor flow. The tensor is this is like tensor flow to the end. And this is the size for each layer. So this is the batch size, because we did not show the batch size. So batch size is how many pictures, because this is for only one picture, one image. But usually we will use a batch size. For example, from the total data, we will get a small batch by batch. Then it will be much easier to use whole data for the matrix calculation. So batch size, and from this batch size, we will update the parameters. So this is statistical gradient descent algorithm in optimization. So before we get this layer, full connected layer, they're all 4-dimensional data. But batch size is the first dimension, and image is second and third, and channel is for the third. Also here is the how many features, right? Feature map, we call it feature map. So how many feature map? Because we use different how many features in a convolution layer. So next we will go to Python source files, and you can download this file from this link. And this link belongs to this website we have with this website for Python and R training. So you go to this site and go to the download link, and you can find the Python machine learning source files link to GitHub. And this link is for donation. If you want to support us for video making, or do me a favor for buying a coffee, thank you. So next we go to Python source file. So we go to this file, and first we set the working directory and load all packages for this source file. Then we can skip some parts of the code because they are just used for learning what is the convolution. We can directly go to the project part. So implementing a deep convolutional neural network using PyTorch. Here, then here we set and loading the data for MNIST handwritten digits directly from Torch Vision datasets. Can load these datasets. Then we set the training data, valid data, and test data. Then we set the batch size for 64 and using data loader class for the dataset for the training and valid, because we use data loader, then the data will be batch by batch, but not them all with one time. So you only load this data for the batch size. After it is used, then for the next data load, next batch size. So it will be not so difficult for computer's memory. Then this is done. Then we can create a neural network model using sequential, then add each layer. So this is the convolutional layer, first layer. You can see the input channel is 1, out is 32, kernel size is 5, and padding 2. Then next is the ReLU. ReLU is for activation. It is a nonlinear activation. So if the value is larger than 0, then use this value. If the value is less than 0, then it will be 0. So this is the ReLU function. And we, after a pooling layer, after these two, then next is another convolutional layer with 32 channel and with the same kernel size 5 and channel, this is input channel 32 and output is 64. This input channel income is the output channel for the first convolutional layer. Then ReLU 2 and pooling 2. We use max pooling with the kernel size 2, so the feature map size will be smaller, but we have different feature map, 64 now, right? Then we will try this part of the model. So first to create this model. Then we will try with X is 4-dimensional data with always 1. We will try it. And we will use the model X, so this means the output from this model and to this layer, right? And we show the shape. So now you can see 4 channel is this is batch size 4, and this is channel 1, and this is the size of this image. Then after this input, after this model running upon to this layer, then we can get batch size is 4 and 64 channel now, because we have 64 feature map for the last layer. And now the size of this map image is 7 for this data pixel. Then we can add another layer called flatten. We have explained that the flatten is to multiply all information for these 3, right? And we will try again for input, same input, 4-dimensional data, and we show how it is the output now. Now is 4 batch size 4 image, and this is 30,136. So the data is 2-dimensional because flatten for these 3 dimensions. Then we add another layer for full connected layer 1 with incoming neural, this number, and output is 1024. And we add another rule for the activation with a nonlinear. Then we will add another layer called dropout. So what is dropout? Dropout is to randomly will close several neural. But here we use the probability of 0.5. So after this running, 50% of the neurons will be zero, will be ruled out. And this will be done randomly. So it will make the model not overfitting for this training data. So it will be better to generalize for the unseen data. So this is the purpose of the dropout. After this one, then we add another full connected layer 2. Then incoming is 1024 neurons and output is 10 neurons because we have 10 digits to classify, right? So we run this part of the code and we set to the CUDA and will be run on the GPU. So we set a loss function, just use a cross entropy loss. And we use the optimizer, Adam optimizer for the model parameters and with a learning rate 0.001. So we define a training function. So here you can see the training for each epoch. This will be the list for loss history for the training and accuracy history for the training and the loss history for the valid data and accuracy history for the valid data. So we start with this list with all 0. And for each epoch, we will set a model train, and for each epoch, we will get batch after batch from the data load data class, right? Training data after data load. So each batch, then we will set this batch to device and we model this batch. So we will get the prediction for the model upon this batch data. So this batch has 64 images. Then we will get a loss between the prediction and the Y batch. Then backward and optimize step and zero correlation. This is just a standard statement here for optimization for the training and update the parameters for the model. Then after this, we will get the loss together for all the batch, and batch by batch they will set and get the how many is calculate correct this job. So after this, you can see after each batch we will get this result for loss and accuracy. Then for evaluation, we will not update the model, just use the results for the training and will do this prediction on the validation data. They will also get the loss and accuracy for the validation data. So after each epoch, we will put this loss accuracy to this predefined for list. So we create this function and we'll call this function. So here we will call this trained model and with number epoch 10 and with the training and validation data. So we run this. It will take several minutes. Because the MNIST data is not so difficult to train, so we can see for about 2 minutes. The 8 epochs are finished. Okay, it is done. Then we can plot the history for the accuracy, and you can see this is the loss and this is for accuracy, one for training and one for validation. You can print out the, we can also use this training model for the test data, right? So here the test accuracy, because this is about 0.99, so very high accuracy. Here we show 12 data, which is for the original image and for the classification. You can see all these one are correctly classified. Thanks for watching.